Welcome to Project Geospatial. I'm Adam Simmons, and here with me in this episode is Nick Weir with CosmiQ. Nick, go ahead and introduce yourself.
Well, thanks a lot, Adam. So I'm Nick Weir. I am a senior data scientist at CosmiQ Works, and I'm also a challenge manager at the SpaceNet LLC.
Awesome. Thank you. And one of the first topics we want to get into with you is because we were on I think a week or two ago with one of your other colleagues introducing us to SpaceNet 6. Can you give us an update of what's going on with that?
Yeah, absolutely. So I just checked the status. The SpaceNet 6 challenge kicked off about a week ago. And for those who are hopping on for the first time and hearing about SpaceNet for the first time here, this is a data science challenge run through Topcoder where we're asking participants to identify building footprints from synthetic aperture radar data, which was collected by and open sourced by Capella Space through the SpaceNet LLC. And so that challenge, as I said, just kicked off. And I just checked and I saw that we already have 11 participants who are currently ahead of the baseline on that challenge. So there are a number of people developing fantastic algorithms for extracting building footprints from this data set, which is really exciting.
Now, can you explain what the diversity in the participants are? Are these individuals? Are these companies? How does that work?
Yeah, historically, it's been almost all individuals. We have had a couple of companies participate here and there, and it's really a globally distributed population that Topcoder brings to the table through their pool of participants. And so we've had winners who come from Japan, Russia, really all over the world, and we have some kind of standard repeat participants, people who are tried and true and have been with SpaceNet since SpaceNet 1 or near that in terms of participating. And then we also have some new folks. And something that's particularly exciting to us about SpaceNet 6 is that it is going to be the featured challenge at CVPR's Earth Vision workshop in June. And so we think having that has probably helped bring in some new folks who might not have participated in one of these challenges before. And so looking at the leaderboard, there are definitely some new names up there, which is always exciting.
So can you go back on that for a minute? What is the Earth Vision workshop, and why choose that as the announcing who those winners are?
Yeah, great question. So CVPR, or Computer Vision and Pattern Recognition, is one of the IEEE's major computer vision conferences every year. It's one of the probably three biggest computer vision conferences that happens each year. And there they have a number of different workshops focused on specific topics. And one of these is the Earth Vision workshop run by the IEEE Geospatial Remote Sensing Society. And they were kind enough to reach out to us and offer to incorporate this SpaceNet challenge as a featured challenge for this workshop, where we will be able to, hopefully we will be able to bring in some participants and have them present their results, how they solved the challenge, how their algorithms worked, and what made them unique in terms of their ability to extract building footprints from SAR, which is really exciting to us, being able to bring SAR data like this out into the open. You don't see a lot of synthetic aperture radar in the open source domain, particularly not really high resolution synthetic aperture radar, which this is. It's half meter resolution, which to our knowledge, this is the only data set that's kind of at that resolution range that's out there for people to work with. And we do also provide, with the training data set for this competition, we're also providing a almost coincident Worldview 2 collect from Maxar, so that you do have some EO imagery, to high resolution EO imagery to look at alongside the synthetic aperture radar. But because what we really want participants to do is to develop algorithms to extract buildings from the SAR data for the test sets, the sets that competitors have to generate predictions against in this competition. there's only SAR. So you have some EO to build your algorithms with, but all you have is synthetic aperture radar for the actual testing case.
Awesome. So what is the so we're focusing on SAR for this challenge, and you mentioned that there isn't enough out there right now. Can you explain some of the industry challenges? Satellite imagery has been out there for quite a while now. Why do you think the industry has taken so long to catch up with SAR?
That's a great question. I think part of it is, there are several issues there, in my opinion. The first one is that small sat SAR is very expensive to do, and it's been pretty challenging for commercial markets and commercial companies to really get kicked off with it. And we're really just beginning to see some companies that are making great progress with that. One of the SpaceNet partners, Capella Space, being one that is really getting started very strong now with that. And so that's been one major challenge. I think the other thing is, honestly, folks outside of government just might not really know what to do with SAR, how to use that really very different kind of data. It's easy to look at an image and say, okay, I understand, how to interpret this. I can look down at buildings just like you'd see in a Google Earth view or a satellite view in Google Maps and say, okay, I know what I'm looking at. When you're looking at SAR intensity values, it's a whole different thing. And I think that it's proven pretty challenging for people to wrap their heads around it. And what we're really hoping is that by open sourcing this data set and running this coding challenge, we're going to provide a good kind of nudge in that direction for folks to start working with this type of data.
Thanks for that overview and clarification. So with SpaceNet itself, can you explain how you select SpaceNet's tasks?
Yeah, absolutely. So as you mentioned, and as we've been talking about, this is the 6th round of SpaceNet challenges. We've been growing this series of competitions over time over the past 3 years. We started out with much more kind of quote unquote simple tasks of just extracting building footprints from EO imagery. And then and that was the first and second challenges. And the third challenge, we moved to trying to ask competitors to extract road networks from these images. In the fourth challenge, we went back to building footprints, and this was a challenge that I actually ran as challenge manager, where we had this really unique set of collects, where we had 27 collects taken over Atlanta during a single pass of a Worldview 2 satellite from Maxar over Atlanta. So everything is almost exactly the same. The images were all taken within 5 minutes of each other, except for the look angle. There were some that were north facing, some that were south facing. And we had collects from almost straight down, just 7 degrees off nadir, all the way out to 54 degrees off nadir, which is, a really substantial oblique angle. And images look very different at that angle than looking straight down at it. And so there we were asking participants to extract building footprints in terms of their actual geo-registered placement from images taken at nadir all the way out to 54 degrees off. In SpaceNet 5, my colleague and the director of research at CosmiQ, Adam Van Etten, was challenge manager. And in that challenge, we went back to road networks, but with a bit of a twist. We asked participants to identify the road network as well as estimates for safe travel speed on those roads. So you have to not just be able to figure out the line for where the road is, but know a little bit more about the surface type, the number of lanes, things like this. Or your model has to be able to generate some estimate for how fast you can travel along this road. He did a lot of really interesting post challenge analysis. That's all in our blog, the downlink, which is on Medium. where really one of the interesting takeaways from that was that algorithms were very good at extracting these metadata properties about roads. If you look at the scores that you'd get, if you were only scoring it against the road network, not caring about travel speed, compared to the scores that you get if you also are trying to take safe travel speed into account, they didn't change very much, which suggests that you're not losing too much performance when you add in this additional feature of safe travel speed. So that was really interesting that worked so well. Another thing that we did with that challenge, and I'm just kind of laying out everything that we've done so that I have a framework to explain how we pick all these things. Another interesting thing with that challenge was that we did not announce what city the final testing of the algorithms was going to be done on before competitors submitted their solutions. So competitors developed algorithms on a set of, I guess, 7 different cities, and 6 different cities, sorry, and then submitted those algorithms. And at the end, we scored their performance on imagery of a city they'd never seen, which turned out to be Dar es Salaam. The idea here is we wanted participants to develop algorithms that worked very well on new imagery that's different from anything that they were initially trained on. Effectively, we want algorithms to be able to generalize to new geographies so that when you apply your algorithm to some new data, you don't have to retrain it on new labeled data for every single city or every single geography that you're going to use it on. And then as we've been talking about, this newest challenge is going back to building footprints, but dealing with SAR. So really what we've tried to do is make small incremental increases to the complexity of these challenges over the course of time, where we don't want to go and make a huge leap and say, okay, we did building footprints. Now let's take some actual disaster data where it's messy. You've got, a ton of occlusion by clouds and things like this, and say, okay, we're going to do a disaster challenge now. Because in our experience, you learn a lot more from making these small incremental increases in the complexity of this. And you get algorithms that, of course, work better because it's not as much of a jump from the existing state of the art to whatever this new task is that we're asking folks to address. And based on that, and then also making sure that we have really good, rigorous quantitative metrics that we can use to score how well participants in the challenge's algorithms worked, allows us to make kind of pretty strong assertions about what worked well and what didn't. We get these pretty robust solutions, and we've made really good progress. We went from doing EO, building footprint detection, 2.5 or 3 years ago for our first challenge, to now we're doing building footprint detection on a modality that's never been open source before, really, which is high resolution SAR, 3 years later. So as we see it, we kind of try to make these very small incremental increases. This allows us to get algorithms that work fairly well, clearly not perfectly. At present, the leading score is essentially a 37 out of 100 in this challenge, I believe. Actually 39 as of this morning, which is clearly imperfect in terms of getting buildings out of the synthetic aperture radar data, but it's still something that's kind of accessible. You can develop an algorithm that kind of works, and you can then you can iterate on and continue to improve on over the course of time. The other thing that's really important to us, of course, is trying to figure out what tasks are of interest to the geospatial community, and this includes folks in humanitarian assistance and disaster response scenarios, whether they are in government or NGOs, or in some other organization, or folks in government in terms of other applications, or small startups that are developing geospatial software.
How do you solicit that type of feedback from either industry or government who may have an interest in influencing? Hey, this is our problem sets, and you outlining what that challenge could shape to help out with that.
Yeah, it's a great question. We do a ton of outreach all the time. Before, during, and after challenges, we will go and speak with as many different stakeholders as we can in a variety of different organizations. We present at a lot of conferences to talk about our lessons learned from past SpaceNet challenges. And we often get a lot of interest from that, and that can spur additional conversations about what kinds of tasks we're thinking about addressing next. And so that's certainly one way where we get a lot of investment from other organizations who are trying to understand maybe they have some very specific problem set or task that they're trying to address, or maybe they like us just have a vested interest in kind of continued growth and improvement of geospatial machine learning and geospatial analysis. The other thing that has made SpaceNet really good at developing this process is the partners in the SpaceNet LLC. So SpaceNet is it's a nonprofit partnership. It's run by CosmiQ, and then there are 8 additional partners. Let me see if I can get them all.
One, though, didn't you?
We did just add one, so yeah, I'll mention that. So we've got Maxar Technologies, Amazon Web Services, the Intel AI Lab, Topcoder, Capella Space. I am going to make sure I don't miss anybody here as I go to. Yep. Let me see. Topcoder, Capella Space, and then as you mentioned, the IEEE Geospatial and Remote Sensing Society joined us fairly recently, and then just last week we were able to announced that NGA, the National Geospatial Intelligence Agency of the United States, has joined as a SpaceNet partner.
I'm surprised it's taken them so long to join the club. That's you would think they would have been one of the first.
I mean, we've had tons of engagement with NGA over time, and they've been very helpful in helping us understand what current state of the art is, what the problems are, and how we can help government with through SpaceNet. And we were really excited to have them join as a partner just last week. So all this is to say, all of these organizations are very deeply rooted in geospatial analysis, remote sensing, computer vision, et cetera. And so they have all been able to provide really invaluable insight into what some of the challenges are and how we might be able to address them with SpaceNet. And then also providing things like data, analysis, expertise, et cetera.
I believe Jake a couple of weeks ago touched on this, but a little bit. But can you talk about what happens with the winners or the participants' data after the fact?
Yeah, absolutely. So we provide cash prizes to the top 5 participants in the challenges, totaling $50,000. And per the terms of the competitions, the participants give the top, usually 5 or 10 participants, give us their algorithms, which we then open source. We make it completely available to anyone to use. It's all, let me see, I think so far we have open sourced, I think it's 23, it might be 28, either 23 or 28 algorithms from previous challenges, which can all be found on the SpaceNet Challenge GitHub page. And so we make those available. We also do a lot of our own analysis where we will take participants' code and their solution outputs, compare them against one another to try to understand what worked well and what didn't, and see what was different or similar about the performance of different solutions and why. We write a lot of analysis blogs about this, again, on Cosmic's blog, the downlink, which ends with a Q instead of a K, on Medium. And so I definitely encourage listeners to go and check that out if you're interested.
And we'll include that in our show notes as well.
Thank you.
So these assessments you do on the participants' data, does that influence the assessment influence how you pick a winner as well?
Well, so with how we pick winners, it's based exclusively on the established numerical metric that we provide to the participants before the challenge even begins. So we make it very transparent. This is going to be the metric that we're going to use to assess how good building footprints are, say that your algorithm developed or your algorithm predicts, and whoever can get the best score against this metric on a held back set of imagery that the participants won't have seen, but nonetheless, whoever can do the best on this held back data set will win. And so the other thing that we do is we do constrain how long participants' algorithms can take to train and then generate predictions, because we want to make sure that we're not just getting very, very large models that would take far too much time to run to generate predictions or to learn based on new data. So the combination of the quantitative metric of how good the predictions are, as well as constraints on how long algorithms take to run, are how we pick winners. Okay.
No, awesome. And so I want to take a step back from the SpaceNet 6 challenge a little bit, and I want to kind of touch on the general geospatial industry here. And from your point of view, can you talk about the challenges in applying machine learning to geospatial?
Yeah, definitely. And this is something that is becoming more and more apparent as more and more people are starting to work on this. And that's really exciting. That's exactly what Cosmic has been trying to do, but particularly what the SpaceNet partnership has been trying to do is get more people working on these types of challenges. So the vast majority of machine learning being applied to geospatial is what we call computer vision, where you're training algorithms to look at images and generate some form of prediction from these images. And computer vision's been around for a long time. This is something that's been worked on since the 50s, if not earlier, and it kind of came into a whole new phase in the early 2000s to like 2010, when neural networks and deep learning started getting very popular. And computer vision as a field, people who work in this are generally working on things like photographs of cats and dogs, or there's a lot of work being done on autonomous driving with computer vision, or security camera footage, or things like this. So all of these are images that are taken, more or less from a ground level, looking horizontally out at some object or set of objects. And they're almost always RGB images, or just a black and white image of whatever object is being visualized. And this is very different from satellite images. Satellite images are frequently not your standard RGB band patterns. You might have a multispectral image that has 8 bands. You might have a panchromatic band, which is not your standard black and white by any means. Or you might have something like synthetic aperture radar, where it's just completely different. And then, in addition, objects are very, very different in their size and their density in satellite images. You tend to have much smaller objects that you're trying to identify from overhead imagery because you're looking down at things from far away. They look a lot smaller, and a lot of the times they're much more closely packed together. If you're trying to identify all the homes in a suburb or something like this, you are going to have hundreds to maybe even thousands of objects in a single image, which is very unusual for standard computer vision applications. So, and then finally, satellite images are enormous. We're talking tens to hundreds of megapixels a lot of the time, compared to the much, much smaller, 512 by 512 or something like this that you're dealing with for so-called natural scene photos taken with a camera phone or something like this that are being analyzed. And so all this is to say that there are massive differences between satellite images or other geospatial data and standard targets of computer vision. And it's been really challenging to try to take these algorithms that are fantastic, that have been developed for these natural scene types of data, and figure out a way to mold them to work for satellite imagery. And that's something that our participants in the SpaceNet challenges have become very adept at. But it's something that's still very challenging. It takes a lot of extra code. It takes making some assumptions about your data, for example, assuming that you can split it up into smaller pieces, which isn't always true for satellite imagery, and generate just as good predictions, et cetera. So this is kind of the set of challenges that, as I often think about them, for applying machine learning to geospatial, is figuring out how to either take these algorithms that have already been developed for other types of data and figure out how to make them work against geospatial data, or finding ways to develop totally new algorithms that are specifically designed for working with geospatial. And that's also an area where some folks are beginning to do excellent work. One great example is the Road Tracer project out of MIT.
What is that?
That's an algorithm that was developed for extracting road networks from satellite imagery, and it was specifically designed for handling satellite imagery data, it's just one great example of some of the steadily growing amount of work that people are doing with developing machine learning tools that are specifically designed for working with geospatial data.
Okay. So what about the struggles with obtaining training data? You also mentioned how hard satellite data is because of how many pixels it is.
Yeah.
There's a different beast than just regular photos, right? But just how expensive it is as well. Yeah. How hard is it to obtain training data?
It's very hard. I mean, this is why one of the reasons why SpaceNet was created in the first place a few years ago, and this is before my time. And so credit definitely needs to be given to Ryan Lewis, Dave Lindenbaum, who used to be at CosmiQ and is now at Accenture Federal, Todd Bakestow, who's at Maxar, and the various other folks who really got SpaceNet up and running in the beginning, is they saw that there just weren't very many high quality training data sets out there for developing machine learning algorithms on geospatial. So that's part of why we generate these large data sets and insist that they be open sourced under a very permissive license that allows commercial use as well as academic, nonprofit, et cetera, use of the data. But that's really just one part of it, is the imagery itself. So when you're developing machine learning algorithms, you need to have labels for the objects that you're trying to teach the algorithm to identify. In the case of going back to natural scene images, this might just be a label that goes with each image saying what type of object is in it, a cat or a dog or a person or a bicycle or whatever. In the case of what we're trying to do, if you're trying to identify building footprints within the images, you need to have every single building footprint traced in the image that you're teaching your algorithm with. And so we now, at this point, across all of the SpaceNet data sets, have about 900,000 building footprints that have been manually labeled in the process of generating these data sets, and we've released about 3/4 of those labels over the course of time while holding
How do
back.
you get to label that at that scale?
Yeah, it's something that we generally contract out in the process of generating the data sets. There are some great expert labelers for geospatial but it's really expensive, of course, to generate these data sets. And so, as you were saying, it's prohibitively expensive for many teams, particularly academic research groups or maybe newer startups who are wanting to just explore this and see whether or not doing some geospatial machine learning would be viable or not. It's a huge investment from a financial standpoint. It makes it really hard for folks to go out and try this out. And so that's why we have created and open source these data sets. Now, fortunately, labeling is becoming more and more popular business model. There are more and more labeling companies that are starting to do this type of work, and we're seeing some begin to show up that are pretty good at doing this for geospatial applications. So we're hopeful that this will get less expensive, get to be something that's more feasible to do at scale. But you still need to have individual people who are used to looking at satellite imagery or whatever your modality of interest is, who can then label every single object manually at present. So,
okay. So just to evolve that into the next level here, for what I'm really curious about is I've had a lot of discussions with companies over the years and talking with machine learning projects. And I think some of the struggle is helping imagery companies, especially some of the traditional ones out there, understand what the requirements are for machine learning actually is. So we have a ton of imagery data. We have a traditional business model where you buy images, coin operated methodology. But there's this emerging business out there for this need for tons of machine learning data. But I don't want to give it all out as an imagery provider. What do I give people? And is there some type of requirements list out there to help companies with data and content try to develop some type of business model to help out?
Try to develop business model in terms of selling data for training machine learning.
Exactly.
Models, yeah, that's it. I mean, that's a great question.
And that's an open question. I don't expect you to necessarily have the answer, but it's a conversation piece.
Sure. No, that's a great question. A standard like that, to my knowledge, doesn't really exist, and it's something that would be great to develop, and it's really important. I mean, something that gets lost, I think, and that might not be quite so apparent from the outside, is that we, with SpaceNet and generally in our other work as well at CosmiQ Works, we have extremely high standards for how well labeled something has to be. We need every single building labeled. You can't just label half of them, because how is an algorithm supposed to learn what is and isn't a building if only half the buildings are marked in an image? And I think this is something that gets lost a lot, is how well things really need to be labeled, given current algorithms that are out there. There are people beginning to develop algorithms that can handle less well-labeled data sets, but I think that's probably at least a few years away in terms of being applicable to an actual problem and not just being research. And so in terms of the amounts of or the quality of labels that need to be generated, as well as how expensive it is to do this labeling. I think the absence of good information in those two areas has made it really, really tricky for imagery providers to figure out how to develop these kinds of products.
Okay, no, that's as good as answer as any. It was open-ended. On a similar note, though, how about as more of these machine learning algorithms are being developed, more of these training data is being explored, and the different types of imagery out there with how about some type of guide to understanding, hey, at this resolution, I can see these things. At this resolution, I can detect these things with these types of algorithms. Something like that isn't developed by the community? And that's
a great question. That type of thing is something that CosmiQ Works is essentially actively trying to develop for a variety of different types of things. There, for example, a colleague of mine, Daniel Hogan, who's a data scientist at CosmiQ, did a study on essentially the amount of training data you actually need to train an algorithm to achieve different fractions of its, optimal performance. So what if you take a full data set of imagery over one city for building footprints, train the algorithm with that, and then you cut that data set in half? What fraction of the performance are you going to get? And then cut it in half again, et cetera. So that's kind of one side of that question. Another aspect of it is definitely what kinds of objects can you see at what resolution? That's a pretty tricky question to address with data that's out there right now. You've got kind of a few different ranges in terms of resolution. You've got, aerial that'll get down to like 7 centimeters or something like this. You've got this very high resolution stuff from Maxar that'll get down to 30 centimeters. And then, there are a couple other things in the sub 1 meter range, but then you've got kind of a gap before you get to the next range of resolutions that you can get commercially for EO, before you get to like planets, Dove satellites and such that are in the 3 to 5 meter range. And then you've got another big jump before you get up to big US government satellites, which provide tons of totally free data, which are great, but they're frequently
about satellites like Landsat or
exactly Landsat, Sentinel, MODIS, etc. And those are all, but that's all over 10 meter resolution or worse. And so it's really hard to figure out exactly where the cutoff is at present. Like, you need better than 2 meter resolution to see buildings, or that's just a random example. I don't know if that's true or not. And in fact, some of Planet's work would suggest that isn't true. And so it's a tough task to explore. It's something that we are trying to get at through the SpaceNet challenges. Like, I'm saying, can you identify buildings in, how small are the buildings that you can identify in worldview imagery, for example? And that's an analysis that I ran after the SpaceNet 4 off-nadir challenge, where I looked at the performance of all the winning algorithms versus the size of the building in the data set, and saying, where did they start to fall apart? And similarly, how far off nadir can an image be taken before an algorithm stops working? So this is a long way of saying that these are kind of questions that are starting to be picked at from a few different angles. But there certainly is not a well-assembled set of thoughts on what works well, what doesn't, and part of this, I think, is because algorithms are improving so quickly that by the time you wrote such a thing, a good chunk of it might not be correct anymore, which is exciting in a lot of ways. I think algorithms are getting better and better at identifying smaller and smaller objects based on our experience from the SpaceNet challenges. the first challenge we ran, the winning score was below a 0.3, which, is just some arbitrary number, doesn't necessarily need to mean anything, except that in by the fourth challenge, which was run 2 years later, the best score was about a 0.75 on a similar type of data. So algorithms are improving quickly. It's kind of difficult, except for a few specific aspects of the question of, what can and can't algorithms do to really give a good answer. And it takes a lot of work to get those answers. So it's still being worked on.
Okay. No, perfect. And once again, I'm putting those questions out there, not for you to answer, but as a discussion and for something that everybody who's watching to think about too. Machine learning is, I would still say it's still emerging with satellite imagery, especially. It's still a challenging issue. And so I want to leave that topic with this question before we move on to the next is what do you want to see accomplished in machine learning as applied to satellite imagery over the next, we'll call it 5 years? What?
Yeah, that's a great question. So I think,
and I left you with the stumper there. That's
a great question. I think something that I'm excited about is just folks in the geo domain kind of becoming more comfortable with thinking about machine learning outputs and understanding when they might work and when they wouldn't. So this isn't so much, what's a specific task that machine learning might be able to address in this amount of time, but just more generally, I'm excited to see people getting more and more comfortable with, taking a machine learning output, recognizing it's not going to be perfect, and then trying to understand where its failure cases are, where its success cases are, and trying to learn how to incorporate that into their own workflow. Whether this is a geospatial analyst who, maybe has hundreds of thousands of images that they need to process to try to identify some specific object or something like this, and maybe they have an algorithm that can find it, 70% of the time that it's there, and that analyst then figuring out, okay, how can I take this algorithm's outputs and integrate that into my workflow to make me more efficient.
So having the community be more culturally accepting and take advantage of machine learning within their workflow over the next 5 years.
That's right. And just having folks kind of begin to understand how to think about these outputs, kind of recognizing that they're not going to be as perfect as a human in most use cases, but understanding how to think about what works well and what doesn't with your machine learning output, and then integrating it thus. Yeah,
that's great. That's a great answer. So within our final topic I have, unless you have anything else,
sure.
I want to get into what other projects that CosmiQ has going on.
Yeah, absolutely. So I mentioned something that we just wrapped up fairly recently, which was Daniel Hogan's data robustness study, as he called it, or as our team called it, the essentially assessing how much training data you really need to train a machine learning algorithm on geospatial data. Another thing that we are actively working on is a study called Rare Planes, which my colleague Jake Schermeyer, who you had on the show a couple weeks ago, has talked about a little bit and blogged about a little bit, where we're doing a little bit of work with a large aircraft data set, looking at how well algorithms can find rare objects, specifically rare types of aircraft, and how synthetic data can improve the ability of those algorithms to perform. Can you kind of augment real imagery with synthetic data, in this case generated by a gaming engine, to improve an algorithm's performance? And something that I'm working on kind of as side project in that is figuring out ways to use a machine learning method called domain adaptation, where you take data, in this case synthetic imagery, and make it look more like data from a different type, in this case the real imagery, or vice versa. Figure out how to use that type of method to potentially improve the utility of synthetic data. So that's
maybe taking an EO image and making it look a lot like SAR, or vice versa.
That's another great example of domain adaptation, and that's actually something that folks have worked on a bit in the SAR domain and the SAR EO domain, and something that we would love to see people do with the data set that we've just released. So if anyone who's listening wants to explore that more, we definitely encourage it. So those are a couple things, and then one other thing that I'm pretty actively working on is this Python library that CosmiQ Works is open source, called Solaris, which is a library for integrating geospatial workflows and deep learning. And as I mentioned before, there's a lot of work that needs to go in on the front end to get geospatial data into formats that'll work for machine learning. And then after you've run a machine learning algorithm, to take those outputs and then convert them back to something that might be useful to a geospatial analyst. And so we have developed this open source library that completes that entire pipeline for segmentation tasks. And the idea being, you can go into this with as little expertise in computer vision or geospatial as you want. All you need to know is some Python, and while still providing the flexibility for folks who are really deep into the weeds to tune functionality to their needs. So that's a library that we've open sourced. It's on GitHub under CosmiQ. Yeah.
Okay. If you want to send me that link, I'll also include that in the show notes as well.
Absolutely. Yeah, I'll definitely do that.
Is there any other last minute plugs you'd like to give, either CosmiQ Works or the SpaceNet challenge itself?
Yeah, I mean, so if there's anyone listening who wants to learn more about the SpaceNet challenge that's running, I would definitely encourage you to check out topcoder.com/SpaceNet or spacenet.ai. Those are the places where you'll find all that information. And even if you're not interested in the challenge itself and you just want to get a hold of the data and play around with it, the spacenet.ai link will give you all the information you need about where to get that. The data is all totally free to download, thanks to the Amazon Web Services Open Data Program. I don't think I've got anything else to add. So thank you so much for having me here, Adam. I really enjoyed this.
No, Nick, it's been a great pleasure, and especially talking about your insights, not just from the SpaceNet 6 challenge itself, but your insights into the community as a whole. Machine learning topics have been, I think, enlightening for folks who are wondering not just what machine learning is all about, but just what the challenge and obstacles have been with the community, and why, even 10, 15 years into this, I know it sounds like we talk about machine learning a lot. It's a buzzword that goes along, but it's a hard problem, and we're still trying to make it work in a lot of different levels. And so, watching the SpaceNet 6 challenge evolve and seeing how it's getting involved with SAR data now is very encouraging and progressive, I think, for the industry. So,
great, thank you. Yeah.
Yeah. Once again, I'm Adam Simmons of Project Geospatial, here with Nick Weir, Senior Data Scientist at CosmiQ Works and Challenge Manager at SpaceNet. Thanks everybody for listening. We'll see you next time.